Today, we're going to talk a little bit more about combinational logic. So we'll start at the ebook homepage and then go to the combinational logic page. Let's just walk through all the things we've been talking about in the combinational logic section. Note that there is a handy summary that enables you to quickly understand the core contents of this section at a glance. Make sure you've spent some time looking at that, and we'll also review that in this video at the end of the lecture. We talked earlier about what modules are. Modules are essentially black boxes. I wanted to point out a couple details since we've discussed this earlier. Notice the data type of almost everything we do in Verilog is a logic type. Logic types can be 0 or 1. It can also be X or Z, an undefined or high impedance. All the time when we're synthesizing, everything will synthesize as 0 or 1. But there are times when using an undefined value, for example, can give the synthesizer some flexibility in the logic that it creates. So define all your variables, all your inputs, all your outputs as a logic type, because that physically models the ones, the zeros, the X's, and the Z's that are produced electrically when we're using digital logic. I also wanted to point out that the assign statement is something we'll be using quite a bit. It allows us to put in a single line that implements something in Verilog. We're also be using continuous assignment blocks, the always comb block, which we'll look at a bit later as we look more into the case statements. Let's spend a moment and think more about operators. Again, System Verilog supports a wide number of operators. They are very C-like. Let's look at the operators available per the spec. Notice this link does take you to the official specification for the System Verilog language. It's something that's released by the IEEE. And here you can see that most of the operators that you've used are available, but notice there are some additional operators. For example, later we'll talk about the difference between logical shifts and arithmetic shifts, and notice that there's a triple less or greater than sign next to a shift. We've talked earlier, and we'll review again, the conditional operator, which is great for synthesizing muxes. There's a handy XNOR, or sorry, yes, XNOR operator, in addition to the standard XOR operator and a couple other things. We'll also spend a little bit of time distinguishing the logical negation operator from the bitwise negation operator. And we'll talk a little bit about the other and or logical operators. But this gives you a good overview. And for details, of course, following this later in the spec tells you everything about what each of those operators do. And I encourage you to take a look at the spec so you better understand what those operators mean. Speaking of operators, let's look at implementing the NOR operation. One important note that I added is, as mentioned earlier, distinguishing the bitwise operator from the logical operator. And you'll see it here in the text, and I thought I'd illustrate that briefly here during today's video. The bitwise operator operates mostly like you would expect. For example, if we take the bitwise negation of a 4-bit number encoded in binary 0101, then we get what you would expect. We get another 4-bit number 1010. You'll notice what this tilde operator, the bitwise negation operator does is taking each one of these bits and flipping it 1 bit at a time. That's why it's a bitwise operator. In contrast, you'll find that the logical negation operator will take the same value, treats the entire number as a true or false value. So in the eyes of the language, this value is true because it's non-zero. So I could equivalently say that's a non-zero true value. And what's the opposite of 1? The logical negation, not the bitwise negation of 1. Well, that's, of course, 0. So be careful when you want to flip bits, when you want to use a NOT or an inverter, make sure to use this operator, the bitwise negation operator. When you truly want to treat an entire value as true or false, then the logical negation operator is the one that you want. I wanted to illustrate that difference because it is a very important difference, and in fact, in solving the revised problem, I've changed this problem so it now takes a 5-bit number. You're required to use the correct operator, which is the tilde operator, to solve this problem. Moving on, again, just be reminded that the assign statement is perfect for producing small amounts of code. As I mentioned later, if we have a large amount of code, we can use a continuous assignment block. But assign is perfect for just a few short and simple assignments. Here in operators ex3, I did want to point out that, again, we're going to use this logic data type to declare a bit, a 0, a 1, an x, or a z, and we can use it to define these variables like this. This half adder carry out variable is simply the graphical name in our schematic of this local variable declaration given right here. Think about variables as wires. They simply route a value from one place, in this case the output of an AND gate to the input of an OR gate, from one place to another, and give us a nice way to refer to that. Use those local variables. They don't have a cost. In other words, it really is just a wire in terms of the resulting synthesis, but it does make the code more understandable and just helps you connect things. Local variables are a powerful feature. Going to the next exercise, I've added a bit of text just to explain the use of logical operations. Notice that Verilog does have a really nice set of both relational and equality operators. The less than, or equal to, and again there's a spec that shows you the full list. Typically you're used to using these operators in if statements. We'll also use it in the question mark, colon, or conditional operator. But another use that's really common in Verilog is to assign the value of a relational operation to another variable. So if we have a single bit variable, remember our handy logic data type called isLess, I can assign isLess to value less than 5. That's going to be 1 if value is less than 5. It's going to be 0 otherwise. And this is not just something unexpected about the language, but it is defined by the language itself. So you are encouraged to use this when appropriate. You'll find this many times a very helpful and handy tool. You're computing a carry bit, you're looking at some is0 value. Don't hesitate to assign the result of a comparison directly to a variable, a single bit variable, because it always produces a value that's 1 if true and 0 if false. If you haven't yet completed all these exercises, I encourage you to do so as soon as possible. Remember that this will help prepare you for the quiz. This will help prepare you for the test. I also encourage you to not use LLMs such as ChatGPT to solve these exercises. These are designed to be small, simple, self-contained opportunities for you to understand the language itself. When you use an LLM, you're no longer understanding the language, you're just looking up answers, and that will not serve you well in the context of an examination. In our next video, we'll talk a bit more about the language, starting with modules.